this lecture video, I shall discuss on digital to analog converter with binary weighted registers and digital to analog converter with R2 to R registers. So first, let's see uh, digital to analog converter with binary weighted registers. Here, this particular figure shows a digital to analog converter with binary weighted registers. The binary weighted registers, in the sense, here we can see each registers have a different weight. First register value is R, the second one is R by 2, third is R by 4, and fourth is R by 8, and so on. As the number of bits increases, the weight of the register also varies. Hence the name binary weighted registers. Op-amp is connected in inverting mode. It can also be connected in non-inverting mode. Here, op-amp is connected in the inverting mode, in the sense all the inputs are connected to the inverting terminal of the op-amp. Hence, we call it is operating in inverting mode. So you can see at the output, the value of output is a phase shifted version of your input values. Hence, we call it as inverting. It can also be connected in non-inverting mode. Since the number of binary inputs is 4, here we have 4 binary inputs, and so the converter, this particular converter is called as a 4-bit binary converter. Because of this 4 particular bits, have 4 bits, and so there will be 16 combinations, 16 combination of inputs, and we get 16 analog combinations at the output. Four switches, that is B0 to B3, are used to simulate. This B0 to B3 is used for simulating the binary inputs. Simulating in the sense which is used to apply the binary inputs to your circuit. For example, let's consider when bit B0 is closed. That is, when we apply the input 0001, bit B0 will get closed. When it get closed, the voltage across R, this particular R, will be 5 volts, because this is 5 volts, and V2 is 0. Why it is 0? In the sense, according to virtual ground concept, V1 is equal to V2. Since V1 is connected to ground, V2 will also be 0. So the voltage across this will be 5 volts minus this 0 divided by uh, uh, 10 kilo ohms, gives you the current that is flowing through this particular resistance R. So we get zero point 0.5 milliamps that is flowing through resistance R. So here we can see this is the current that is flowing to the input terminal. So this current will get split across IB and IF, that is through feedback. Since the input resistance of the op amp is very high, that is in terms of mega ohms, no current flows through the op amp, or a minute current flows, which is negligible. Hence, most of the current, that is zero point 0.5 milliamps, flows through the feedback resistance. When it all the current that flows through the feedback resistance. So here the op amp is working as a current to voltage converter. Hence, the current, this particular current, zero point 0.5 into this 1k, gives you 0.5 volts at the output. When the switch B0 is closed, we get zero point 0.5 volts at the output. Let's consider now B1, switch B1 is closed, and B0 is open. When B1 is closed, uh, the action closes when B1 is 1. This closes this particular switch. When this particular switch closes, then a positive of 5 volts is applied to this particular resistor. When we apply this 5 volts to this particular resistor, we get the current that is 1 milliamps that will be flowing through this particular resistors. That is, the current gets doubled. So this current flows, this 1 milliamps will flow over here. So since, as I told, input resistance of the op amp is too huge, no current flows, so it will be 0. So the entire 1 milliohms, sorry, 1 milliamps will flow through this particular feedback resistance, and the output voltage will be minus 1 volts when switch B1 is closed. If both switch B1 and B0 is closed, then we get the output voltage of minus 1.5 millivolts. So depending on whether which switch is closed or open, so based on which switch is closed or open, according to that we get the output voltage, output voltage. So hence the binary inputs will be converted into an analog voltage at the output. So the sum of these currents is equal to the current through RF, as I told, as the current that flows through RF, which in turn is converted into the voltage. So the output what we get is defined by the equation minus RF into B naught by R plus B1 by R by 2 plus B2 by R by 4 plus B3 by R by 8 into V reference. So this figure shows an analog output versus possible combination of inputs. So this is the analog output what we get, and these are the possible combination of inputs what we are applying. So for 0, all bits are 0, or when all the bits are zeros, then all the switches will be in the open circuit condition, and the output will also be 0. When B0 is closed, we get zero point 0.5 volts, and when B1 is closed, we get 1 volts. When both B1 and B2 is closed, that is we get 3. So for 3 it will be 1.5 volts, and so on up to we get 15. So for 15 the maximum value is 7.5 volts. uh, so for each step you can see here, for each step the voltage is getting increased by zero point 0.5 volts. Zero point 0.5 volts. Here the problem what we get is the required binary weighted registers. So we won't get the exact value of the weighted registers. As the number of bits increases, we won't get the exact weight of the registers. That is the problem. So alternative what we can do is we can go with R2 to R register, since it requires only two set of precision registers. So in this particular circuit, you can make use of metal film resistors for better accuracy. Here we make use of metal film resistors for better accuracy. So the desired step, whatever step we got, that is zero point 0.5 volts in this particular circuit. So that particular step can be varied by choosing a proper value of RF. By choosing proper value of RF, we can get the desired value of steps. Whatever steps we required, that steps we will get. The next one is the R2 DAC with the R2 to R register. DAC in the sense, as I told, a digital to analog converter with R2 to R register ladder. So the binary inputs are simulated by here, as the binary inputs is simulated by switch B0 to B3, and the output is proportional to this output. This particular output is proportional to the binary inputs whatever you are applying. The binary inputs can be either high or low. So high or low in the sense, whenever this is connected to this particular pin, this will be connected to 5 volts, and when this is connected to this pin, it will be 0 volts. So whenever this particular bit is 1, then it will be connected to 5 volts. If this bit is 0, then it will be connected to ground. So the input can be either high or low based on the bit what we are applying for conversion. Assume for example, let's assume we are the MSB bit, this particular B3 bit is connected to 5 volts. That means we get we are applying input which is 1000. When we apply 1000, then B3 bit will be connected to 5 volts, and all other bits will be connected to ground. So if we apply a Thevenin's theorem, Based on Thevenin's theorem, we get this particular equivalent circuit. So how we get, in the sense, in the previous, you can see here we have R, 2R, R and 2R resistors in each branch. So the name R to 2R. So since only this branch is connected and all other are connected to 0, you can see this and this resistors are parallel. That is 2R parallel with 2R. So this will be in series with R. So this value will be again in parallel with 2R. That is what we get here. So here you can see 2R parallel with 2R, that will be in series with R, and this R is again parallel with 2R. So this 2R is will be in series with R, and this entire thing will be in parallel with 2R, and again this will be in series with R. So if you perform when you calculate these things, we get the Thevenin's equivalent resistance, which will be equal to 2R. So here we get Thevenin's equivalent resistance as 2R, and bit B3 is connected to 5 volts. So this will be the Thevenin's equivalent circuit. Uh, Here the inverting input is here this particular inverting input is connected to the input terminal, hence this is in the inverting configuration, inverting mode. Uh, this particular voltage V2 is 0 because of virtual ground concept. Since inverting terminal is connected to ground, the voltage across V2 will also be equal to 0 because of virtual ground. Hence, the potential across this point will be V2. So here also it is 0 volts, and here also this it is connected to 0. Therefore, the current through this particular resistance RTH will be equal to 0. So the total current what is flowing in through this particular circuit will be only through because of this resistors or this particular bit. So here the voltage what we apply is 5 volts. 5 minus 0 divided by 20k is the current I. So we get 5 divided by 20k will be equal to 0.25 milliohms, milliamps. So 0.25 milliamps will be the total current I. This current will be split across the inverting and terminal and the feedback resistor. Since this particular inverting terminal will be having a huge resistance, or input resistance is infinite. For an ideal op amp, it is infinite. For no current flows, so the entire I will flow through the feedback resistance. So we get when all the current flows through a feedback resistance RF, we get 0.25 into 20k will be equal to minus 5 volts. So we get minus 5 volts at the output. So advantage of if you see the output voltage for different combination of inputs is given by V0 is equal to minus RF into B3 divided by 2R plus B2 divided by 4R plus B1 divided by 8R plus B0 divided by 16R. So based on the what combination of input bits we are applying, based on that we get the output voltage. So here, what is the advantage? In the sense it requires only two set of precision resistors, that is the value of R and 2R, and it requires more resistor, and is more difficult to analyze than the binary weighted resistor type. As the disadvantage, when we see the disadvantage, it requires more number of resistors compared to the previous one, that is uh, binary weighted resistors. When we compare this particular R2 to R with the binary weighted resistors, the number of resistance required for this particular circuit will be very large, or more number of resistors is required. And as the number of binary inputs increases beyond 4, and both digital to analog converter circuits get complex. Both this particular circuit and that is R2 to R and binary weighted resistors, both the circuits becomes complex. So these two are the disadvantage of this particular circuit. And so here we can, this shows the input versus the output, and the step size, and the step size. Here, as I told, the output voltage corresponds to the possible value of input bits what you are applying, and here we get a maximum voltage of minus 9.375 volts. So for individual bit, what will be the output voltage is shown in this particular table. So for all zeros, the output will be 0. When bit B naught is 1, B naught is 1, we get 0.625 volts, and when B1 is 1, we get 1.25 volts. When both B naught and B1 is 1, we get 1.875 volts, and so on. When all the bits are 1, we get minus 9.375 volts. So this is all about the R to R and mm, uh, binary weighted DAC. So in the next lecture video, we shall see the successive approximation analog to digital converters.